Hi everyone! If you thought combinations were interesting already, just wait until you learn about all the hidden patterns they create as we explore the mysteries behind Pascal's triangle. Here, we have a set of combination problems. We could calculate the number of possibilities for each one using the combination formula, but that might take a while. Instead, let's see how many of them we can figure out with our reasoning skills. The entire left-hand column involves choosing 0, which might seem like a weird request. If I give you any number of objects and ask you to choose none of them, how many outcomes are there? There's only one outcome, the outcome where you choose nothing. Any combination involving choose 0 will automatically have only one outcome. In the same vein, what if I give you a bunch of objects and tell you to choose all of them? If these were permutations, there would be multiple ways to arrange all of the objects, but since we're talking about combinations, it doesn't matter what order you choose them. There's only one outcome, the outcome where you choose everything. So any choose all combinations also only have one outcome. Well, that already took care of a bunch of the warm-up, only a few combinations left. What about these two combinations? 2 choose 1 and 3 choose 1. If you are only choosing one at a time, then there is no grouping to do. Each group consists of a single object. Anytime a combination only allows you to choose one option, there are as many outcomes as there are options. And that leaves just one combination left to find. 3 choose 2. This one isn't quite as easy to logic out, so let's turn to the combination formula. 3 choose 2 can be calculated as the number of options, factorial, divided by the number of options left over after choosing 2, factorial. And the amount of permutations per combination of two items. This comes out to 3. So 3 choose 2 is equal to 3. At this point, you may notice something odd. This row is symmetrical, and if you look closely, so are all the rows above it. Why would combination calculations be symmetrical? Let's think about what happens when we choose a combination from a set of options. If we need to choose 2 of these 3 options, then naturally, one option will be left unchosen. Whenever we make combinations, we're actually separating all of the options into 2 groups, the chosen and the unchosen. Because of this, choosing 2 and leaving 1 unchosen will create the same separated groups as if we chose 1 option and left 2 options unchosen. In other words, 3 choose 2 and 3 choose 1 are just 2 names for the same calculation. They'll both have the same number of chosen and unchosen groups. This connection between chosen and unchosen combinations is commonly known as the symmetry of combinations, where any combination calculation is the same as if you were choosing the unchosen amount instead. In fact, we could represent this idea a bit better if we just shift these values over so they're centered. There we go. Now it even looks symmetrical. We could even expand the triangle down further with what we know now. Choosing all or choosing none are symmetrical calculations that each only have one outcome. When choosing only one from a set of options, there are as many outcomes as there are options, and that will be symmetrical with choosing all but one. But what about these combinations in the middle? They aren't symmetrical with any of the combinations we already know, nor can we quickly figure them out through logic. Can you find any other patterns we could take advantage of? Maybe it would help if I added some arrows. Do you notice a pattern now? Each value in the triangle is just the sum of the 2 above it. Pause the video and use this pattern to try filling out the rest of this triangle down to row 5. 4 choose 2 ends up having 6 outcomes. 5 choose 2 has 10 outcomes, and 5 choose 3 is symmetrical with that. You've probably already figured out the name of this secret pattern, since it's the entire focus of this lesson: Pascal's triangle, a never-ending symmetrical triangle of values representing the number of outcomes from combinations, with each row representing the total number of options, and each diagonal column representing the number of choices. Note that Pascal's triangle starts with row 0 and diagonal 0, with the very top of the triangle being 0 options, choose 0. While having 0 options or combining 0 choices are rare, they are still possible, so we can't forget those parts of the triangle. Okay, so cool. Combinations make a neat triangle pattern. Big whoop, right? But remember, the connection goes both ways. We can use Pascal's triangle to calculate combination outcomes without having to use any long, complicated formulas. For instance, if I asked you to calculate 6 choose 4, you could use the combination formula with this long calculation, or you could simply keep building Pascal's triangle until you reach row 6. Then find where diagonal 4 intersects it to find that there are 15 possible combinations. I don't know about you, but I like this method way better. Let's take a break from notes and complete this lesson's first activity: expand Pascal's triangle, so that you have a pre-made copy of the triangle all the way down to row 12. Pause and do that now. Then come back to the video. We still have more to learn about Pascal's triangle. Let's make sure your copy doesn't have any mistakes. Here are rows 7 through 12 of Pascal's triangle. Pause if you need to compare your own copy and fix any mistakes. Make sure to put this somewhere safe so that you can refer to it during the next few lessons. And I bet it'll be a huge help on your unit assessment. Now that you have your own reference copy of Pascal's triangle, let's check out some more cool ways it can be used. There are so many patterns in Pascal's triangle that we can't even fit them all in a single lesson, but let's recognize some of the most notable ones. First, we already know Pascal's triangle represents combination patterns, but that's actually true in multiple ways. Let me show you something cool. From the top of the tree, we could get to the row 3 diagonal 1 location by going left, then right. Or we could go left, right, left. Or we could go right, left, left. You'll notice that the position in row 3 is to the right of one value and to the left of 2 values, just like how each path included 1 right and 2 lefts. This position showed us how many permutations we can make from a combination of 1 right and 2 lefts. More generally, in situations with only 2 options, Pascal's triangle can tell you how many permutations can be made with A of one option and B of the other option. Since the triangle is symmetrical, it doesn't even matter which option is A and which is B. 1A and 2 Bs will have the same number of possibilities as 2 A's and 1 B. Using this newfound pattern, let's try a harder example. In how many different orders could you draw 2 red cards and 4 black cards from a deck? Since we're drawing 6 cards, we go to row 6 of Pascal's triangle, then find where there are 2 values on one side and 4 on the other. Between those, we get an answer of 15 permutations. But why? Because to get to this location, we have to go right 4 times and left twice. We could do that with this path, or this path, or this path, or any of these 15 different paths. The value we found tells us how many different paths there are to end up with 4 black cards and 2 red cards. Now it's your turn. Pause and try these examples in your guided notes. For the first one, 9 total flips means we need to use row 9. We can use either of these positions that have 3 spots on one side and 6 on the other. There are 84 possible ways to get 3 heads and 6 tails. For the second example, we use row 12 for a 12-question test. We find a position with 8 values on one side and 4 values on the other, and find out that there are 495 different ways these true-false answers could be arranged. There's one final, very important pattern in Pascal's triangle, and it all starts with this, a power of a binomial. Before we can investigate how this is related to Pascal's triangle, pause the video and complete the binomial expansion section in your guided notes. Anything to the 0 power is just 1, and anything to the first power just stays the same. A plus b squared will require you to multiply the binomial times itself using the distributive property, and we can do the same for a plus b cubed. Take our previously expanded form of a plus b squared multiplied by a plus b again, and use the distributive property. As the exponents got higher, these required more work to expand, and we can assume this will remain true if we keep going even further. Wouldn't this process be so much simpler if we found a nice, easy pattern we could use instead? Do you notice any useful patterns in these expanded terms? Oh, hey, the coefficients are exactly the same as Pascal's triangle. And of course, the exponents just transfer from a to b one at a time as we move across the expansion. Hey, wait, these are just path permutations. 3 a's, 2 a's and 1 b, 1 a and 2 b's, and 3 b's. This is just Pascal's triangle in a different form. So does that mean that we can just use Pascal's triangle to expand powers of binomials? Let's try it. Expand this expression using the distributive property, then expand it using Pascal's triangle, and see whether the results match up. When we use the distributive property, it takes a while, but we eventually get this. To use Pascal's triangle, we copy row 4 down as the coefficients, then start with a to the 4th power on the first term, and transfer the exponents as we move across: a cubed b, a squared b squared, ab cubed, and finally, b to the 4th power. Look at that! It really does match. Pascal's triangle really is a much quicker method. This means we have a way to expand binomials to really high powers way quicker than if we use the distributive property. Pause and try using Pascal's triangle to expand these two binomials. For a plus b to the 7th power, we use row 7 of Pascal's triangle. A plus b to the 10th power would take a really long time to expand using the distributive property, but with Pascal's triangle, it only takes a couple minutes. Great job! In this lesson, you learned what Pascal's triangle is and how to quickly expand it to any row you need. You learned several ways to use Pascal's triangle, such as quickly finding the number of possible combinations when making R choices from N options. You can also use it to find the number of ways there are to choose from two options or paths a specified number of times. And using that knowledge, you are able to quickly expand a power of a binomial. Speaking of binomials, we now have all the knowledge necessary to understand the binomial theorem. With the video and guided notes done, your next task is to complete the lesson activities and additional practice. Then end this lesson with the online practice. See you next time when we finally get to learn about the binomial theorem.
Hey!